All right, subscribers, welcome back to another episode of Science with Surback. Today we're going to finish out Chapter 9, and this section, 9.4 until 9.8, deals with hybridization in molecular orbitals. So a couple of objectives of these notes is to, one, formulate the bonding in a molecule in terms of sigma bonds and pi bonds from its Lewis structures. Explain the concept of delocalization of electrons and pi bonds in molecules such as benzene, and then explain the concept of orbital overlap and the reason why overlap in some cases can be zero because of that symmetry, and explain the basic concepts of molecular orbitals. We should also be able to describe the principles of valence bond model used to describe covalent bonding between atoms, explain the concept of hybridization and its relations to geometrical structure, and assign hybridization or hybrid orbitals to an atom in a covalent molecule when required to explain its geometry or bonding between atoms. So we have talked about the structure of molecules and the shape they form, and this is really the reason why we have this. So we have this idea, and it's a pretty good idea here, of valence bond theory. And so what happens here is this. We have to think about what's happening during a particular covalent bond, or when a covalent bond is formed. And so what happens here, if we take our couple examples of H2 and HCl, remember what would happen in this particular instance is this. We would have to get the H and the Cl close enough, and once they become close enough, they're going to be involved in that covalent bond, which we eventually show here as the H as a line connected to the Cl. Now, one thing that I want to emphasize here is that, hey, H and Cl have to get close enough together to share those electrons. And same thing can be done with H2. I know I wrote that in reverse order, but H2 can be done in a similar fashion where those valence electrons get close enough together where they can be shared, and we show that bond as that single bond. What we want to do is explain, well, what is happening specifically, and really look into the details of those valence electrons. So let's get going here, and let's think about the things I briefly mentioned just now. So one thing that has to happen as a covalent bond forms is you have to have two atoms get close enough to where they share their electrons. Now, a couple of things to be cognizant of is this. One, as you get two atoms closer and closer, those electrons, those electron clouds are going to begin to want to repel each other. But if you don't get close enough, they won't be able to share. So you have to have this happy medium of where those atoms are in comparison to the other atom to allow for that sharing to happen. And this, again, is kind of the explanation of how we have that. So to make room and to allow for this to happen, we have to have an arrangement or a rearrangement of our orbitals. So with our hybrid orbitals, we have to have them mix to form new orbitals. So we're going to go through several examples here, and we're going to see where this hybridization comes from. Okay. Now we have some sheets here, but the number of hybrid orbitals is going to be equal to the number of atoms plus the number of lone pairs around the central atom. And really the key word here is around the central atom. That is the atom that's making room for those particular electrons to be shared. And we'll see that here in our atomic orbital examples. Now, some other important things here is that the number of hybrid orbitals need to be formed is equal to the number of atomic orbitals that is used to hybridization. It kind of goes along with the law of conservation of mass and matter for those items there. Okay, so what we have, we're going to go through some different examples, and then we'll kind of expand on this as well. But our hybridization is a direct result for what needs to bond. So I'm going to start out here with our BeCl2. And I know it's kind of an odd one to think about because Be we traditionally think as a metal. It is in group 2. But it does help us explain our hybridization here. And so what we do, or what we start with, is we start with our central atom and we draw our Lewis structure. Okay, so BeCl2 would look like this. Now, from the previous page, it said that the number of hybrid orbitals needed is the number of bonds plus lone pairs. So if we talk about the number of hybrid orbitals needed in this particular example, we would count the number of bonds plus lone pairs around just the central atom. So if we do that, we only have 1, 2, and so we're going to need 2 hybrid orbitals. Now, what I also want you to think about here is the orbital box diagram of our Be. So if we think about this, Be would have an electron configuration as such. And the orbital box diagram of Be in its ground state would look like this. Now, what happens is this. We need 2 hybrid orbitals, which is essentially saying, hey, we need 2 spots to connect things to Be. So what happens is this. This electron gets promoted. So I'm going to put down here a little note. Electron gets promoted. Now, this does not come with a pay raise. That's a joke. But it does allow us to do this. It allows us to form our hybrid orbitals needed. And so what happens here is now we have an sp hybrid orbital, where these electrons that I wrote here in pencil are from Be, and then I'll write here in green, this makes room for the electrons from Cl to come in and bond with our central atom Be. And again, this gives us our sp hybridization. Now, another good example here would be carbon dioxide. So if we go into CO2 and we think about this, we have carbon. It's actually double bonded. It's double bonded to our oxygens, and we would get something that looks like this. Now, again, carbon, its electron configuration would look like this. And if we drew the orbital box diagrams, we would get something that looked like this. Now, again, what I'm doing is I'm drawing everything in its ground state form. So again, you see this promotion of our electron, and so I'm going to show that here in red. And what actually happens, because there is our two covalent bonds, what actually happens is that we have an sp that forms for this carbon and oxygen on the right and also on the left. So as a result here, you get your carbon to make that double bond and share with that of oxygen. Just another example. All right, so moving on here to some other types of hybridization. We have BF3 and CH4. So BF3, again, the Lewis structure for BF3 would look like this. Reminder, this is an exception to the octet, so we're going to get this. Again, you can determine the number of hybrid orbitals by counting the bonds plus lone pairs around the central atom. We count 3 here, so that means we would need 3 hybrid orbitals. But specifically where this comes from is as follows. We would get our ground state electron configuration, our hybrid, or excuse me, our orbitals here would look like this. And then essentially what happens here is you promote this electron to allow for that bonding around the central atom. So what you would get is this. You would get 3 boxes to represent that, hey, we, from our boron, have 3 spots to bond, and so the 1 electron from each of the fluorines comes in, and that is what we show here to get our sp2 hybridizations. Now, I want you to apply this concept here to CH4. I'll pause and then you can try this on your own. All right, so what you're doing with hybridization is you're essentially making room in your orbitals to allow for that covalent bonding to occur. This helps us explain, hey, how does an atom get close enough to share these electrons? All right, so one more example here with the hybridization of NH2. I want you to do this one on your own. I'll pause and then we will resume. Okay, so what happens here, we would end up with sp3 hybridization because, remember, this is an ion, so you'd have to add that extra electron, which means in our hybrid orbitals, we need to move over and make room for those particular orbitals. All right, so now, going through this process again, I'm going to have a little cheat sheet there that I can help you out with hybridization. But moving on here to our summary here. When we need to do this, again, the best way to go through this is through our orbital box diagrams. And again, if you think of promoting those electrons or stretching those electrons into the locations or those spots that allow us for the covalent bonding to occur, it really helps us out in this process here. Now, we're going to go down a rabbit hole with what happens as we form that covalent bond. So we've made hybrid orbitals to allow for those electrons to be shared between 2 atoms and make room for all of those needed electrons. Now we get a little bit more in depth and in detail. And so we start out here with sigma, and then we'll move to pi bonds in just a second. But a sigma bond is defined as the direct area or axis in which electrons are shared. So here on our sigma bonds, again, this is that region that I'm circling in red. That is exactly where those electrons are shared between 2 atoms. All right, and I show you a couple different examples. now what happens here is that as atoms get closer and closer, and by having atoms closer and closer, they become closer, and those other orbitals begin to overlap. So as you have overlap that occurs above and below the plane of the nuclei, you begin to develop these pi bonds. So the only way we can get these atoms close enough is in a double and a triple bond. Now, a good little rule of thumb here is a double bond is going to have one sigma bond and one pi bond, and a triple bond has one pi bond and one sigma bond and two pi bonds. All right, so let's go through an example and talk about pi and sigma bonds and identify them. Okay, so number one, it says determine the number of sigma and pi bonds in the following molecule. Well, remember that any direct interaction is going to have one sigma bond. So this H and this carbon will be 1. Then we have 2, 3, 4. And then there's going to be, remember from our little cheat sheet, one sigma bond in a double bond. So that's a total of 5 sigma bonds. And then there is one pi bond in each and every double bond. So we can say that there is 5 sigma and 1 pi bond. All right, so now let's keep moving on here, and let's summarize, let's talk about resonance. Okay, what resonance does here is it delocalizes the pi bond, and that's because your placement of your double bond can rotate. So a great example here is of benzene. So benzene, just as a reminder, is a hexagonal shape with a double bond at every other carbon. Now, it can also be drawn where those double bonds essentially flip places. So remember, where there is a double bond, there is one pi bond. So again, as this happens here, essentially our location of our pi bond flips, and so you delocalize that pi bond, meaning, hey, it can flip around as that double bond flips in these examples. All right, summing this all together here with sigma and pi bond is that every pair of bonded atoms shares one or more pairs of electrons. As a result, you are going to have a sigma bond. So every single covalent bond will have one sigma bond. Pi bonds are when you have that additional overlap. So things have to be brought closer together, and we can delocalize those pi bonds if we flip or we have resonance structures which flips that double or triple bond. All right, so now we need to talk about one more thing here. So we talked about, all right, how do you make room to allow those electrons to come into place for your hybrid orbitals? And then we talk about here, okay, well, specifically, what happens as those hybrid orbitals overlap and those electrons come into place? And then now we can talk about, all right, the specific energy involved in producing these covalent bonds. Because ultimately, remember, we're dealing with electrons, which when they come together, because they're negatively charged, they naturally want to repel. So we have to have some give and take, and that give and take is going to cost some energy. What molecular orbitals allows us to do is it allows us to see the specifics of the energy, and as those covalent bonds are formed and those hybrid orbitals are formed, what's that costing on the energy front? Okay, so what we do, we represent this with diagrams, and we go into a little bit more depth, a little bit more theorized material with this business here. So what we talk about here is this. When atoms get close to each other, they have their atomic radius or their atomic orbitals overlap. Now, what happens here is that we're going to form in these molecular orbitals, and again, this is a theory, bonding and anti-bonding molecular orbitals. And so what happens here, a bonding molecular orbital is lower in energy and an anti-bonding is higher in energy. And so this all occurs, as you saw from the first page of this part of the notes, because of that wave theory of light, and that wave theory was eventually used to help describe electrons. So again, you're getting into the quantum mechanics of things, so we're getting, again, more detailed into this information. And so what happens, the best way to see that is through our diagrams. So here is our diagrams. Remember, what you have here is this. You have our atoms that are involved in the bond, and then this chart right here is showing, hey, what is happening to the energy of those hybrid orbitals, and also what can we say about the electrons involved in it. So it does a couple things. One, talks about energy. Two, it talks about, okay, we form these hybrid orbitals, but there is going to be the difference here in these hybrid orbitals. And we'll get to see these in a couple examples. The best way to see that is just by filling out these charts. So these charts will make a little bit more sense as we go through these notes. Now, the other thing that we need to factor into is the sigma and pi bonds that we just got done talking about. Okay, so the sigma bonds are going to be the orbitals with an electron density in both molecular orbitals centered about the axis. Okay, what this means for us is that, hey, the molecular orbital that forms the sigma is going to be involved in the sigma molecular orbitals. Now, the orbital that forms the pi bond is going to be involved in the pi molecular orbitals. And now your head may be spinning a little bit, but let's take this into an example and talk about what we have here. So we have an example of our molecular orbital diagram of H2. And now remember, H2, if we drew its Lewis structure, would look like this, where we only have one sigma bond because we only have one covalent bond. Now, when our two H's come together and they share those electrons, they are only going to share that one s orbital. And so what happens is that when they come together, they are more stable, and they show that through a less energy. And really, if you want to add this is probably pretty effective to add. The energy increases on this chart as you go up. So this is showing a couple things. One, as we have our hydrogen that's bonded, the hydrogen molecule is more stable because it's lower in energy than each of your H atoms. All right? Now, we're going to get a little bit more into detail with this, and that's talking about our bond order. And so what a bond order is it's defined as half the difference between the number of bonding electrons and the number of antibonding electrons. Okay, well, what that means is we can apply this formula. So we just got done with our example of hydrogen, H2, and I should have pointed something out here, is that on here we had a sigma, and we call this sigma star. And so what this represents is This guy is going to be your bonding, and sigma star is going to be your anti-bonding. And so this can be used for finding our bond order. So if we use our bond order, and I'm just going to abbreviate bond order as BO, for our hydrogen, we look and we say, okay, how many electrons were involved in the bonding? And so these are the ones I drew in red. Well, there's 2. So there's 2 electrons. I'm going to put 2 to the E minus the anti-bonding electrons. Which, do we have any anti-bonding electrons? The answer is no. So we have 0. And so the bonding order would be equal to 1, which holds true for our little cheat sheet here. Now, if we had odd electrons in our bonds, yes, we could have a fraction or something with a decimal there for our bond order. That's a rare case. We'll deal with it on a case-by-case basis. All right, so with this here, we move into some details that help explain our molecular orbitals. Again, just take some time and go through this. It essentially uses our ideas of orbital box diagram and hybrid orbitals, and then applies the ideas that we've just learned about sigma and pi bonding, along with the energy involved for those particular electrons. All right, so what we will do here, we'll quickly go over some examples of molecular orbitals. And so molecular orbitals, again, are just there to show us, all right, what is happening? How could we use this to explain the energy involved in our electron transfer? And so we start out here with lithium. And remember, lithium would have 3 electrons. So I'll show a lithium that's on the left with my red pen, and then I'll show my electrons with the other lithium on, that is not there, that should not be there, with my green pen. And so what happens here is this. Once we form these, we would have something that looks like this. And so with our lithium here, lithium would form a bond that has 1 single covalent bond, and our bond order would be half times the number of bonding electrons, which is 1, 2, 3, and 4, minus your anti-bonding electrons, which is 1, 2. So half of 4 minus 2 would give us a bond order of 1, and that is for your lithium atoms. Now, if we can apply the same thing to Be, we have to think about this. Be has 4 valence electrons, and so this should be 2s2, not 2s1. But when you would have this, you would get the following to happen here. Now, what the important part here of Be, we're trying to figure out, hey, could a Be bond to another Be? Well, the answer to this can be found in our bond order. So the purpose of the bond order is to go through this. We take the number of bonding electrons, which is 4, minus the number of antibonding electrons, which is also 4. And so this gives us a bond order of 0. What this means in our molecular orbital theory is that a Be2 bond cannot exist, and that's explained from this bond order of 1. So that is our whole purpose here of bonding and antibonding orbitals and molecular orbital theory. Now, we're going to go into a little bit more detail here that we will just glance over. All right. So with this, we haven't gotten into anything that has our p orbitals and our orbital overlap here. Again, we're going to go into some details here, but we need to remember this, that in a pi bond, in a double or triple bond, we're going to have at least one sigma bond. Okay, so as you read through these, keep that in mind. Okay, so with this here, as we get into the 2p level, we are going to have a couple of things. We're going to have some odd interactions, and then the other thing too is this. As the bond length decreases and our bond energy increases, that means our bond order has increased. So again, our bond order increases, the bond length decrease, and the energy decreases. And we've done, we need to do this example here. So with our example here of boron, what would happen here is this. We in B2, okay, so let's skip this example for right now, and we will move on to talking about the chart. This gives some data with our bond orders and our bond enthalpy, which is, again, the way we can measure how strong a bond is. So using this, we can correlate our molecular orbital diagram and express energy to what our bond has that occurs. All right, so the last example here, I'm going to go over very quickly, is just talking about how we can express our molecular orbitals to this particular molecule. All right, so again, I'm just going to go over this really quickly, but we're only dealing with the second energy level, so that means we can just deal with valence electrons. Nitrogen has 5 valence electrons, and oxygen has 6 valence electrons. So what I'm going to do here is I'm just going to put these electrons in the locations that we have. Okay, now when we have the molecular orbital diagram for this item or for this molecule, we would have the following. And so what happens here is this. We can help determine, or we can help understand a little bit about the energy that occurs in our NO molecule. Now, just a reminder, an NO molecule would have this Lewis structure. So again, there's our Lewis structure, and what this helps explain, what molecular orbitals help explain is, all right, well, we have a double bond. Why does that double bond, why is it stronger? Well, it's because it requires more energy to break, and then can also help explain, hey, what do we do with an odd set of electrons? All right, so the important thing about this section is hybrid orbitals. Like I said, I'll develop a little cheat sheet to help you understand what that plays a role or what impact that has on molecular geometries and how we can use it to find hybridization. Hope you've enjoyed this video as always, and if you haven't already, make sure you subscribe.